Hello again. Thanks for joining us on another episode of Space Nuts, where we talk astronomy and space science. My name is Andrew Dunkley, your host, and it's good to have your company. Coming up on this episode, we will be doing an update on 3I Atlas. Yes, I did pronounce it correctly this week. We'll also take a look at a few other comets that are skimming around our region at the moment. From comets to meteor showers that are making the news, including the Draconids meteor shower, and the moon of Uranus called Ariel or Ariel is making the news. This is a really interesting story, and we'll be talking about asteroids being thrown at us by Venus in the next few thousand years. That's all coming up on this episode of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And as you would be aware, Professor Fred Watson is on the road or on a plane or on a bus or something, but he'll be away for several weeks. And in his stead is Professor Jonti Horner, Professor of Astrophysics at the University of Southern Queensland, joining us again. Hello, Jonti.
Good morning. How are you getting on?
I'm getting on quite well. What about you?
Oh, not too bad. I've never been a great fan of mornings, but I'm powering through and mainlining coffee and doing all those kind of healthy things to try and be coherent today.
Mainlining coffee. I love that. I should try it. But yeah, it's good to have you back. We've had a few people asking, is he coming back? When will we see him again? Well, today. So great to have you back, Jonti, and we're going to get straight into it because we've got a lot to talk about. And we'll start off with an update on the comet, the exocomet, I suppose you'd call it. I don't know. 3I Atlas. What's happening there?
Well, it keeps getting lots and lots of media, and unfortunately, it keeps getting lots and lots of bad media as well, thanks to a certain astronomer in the US who should probably remain nameless, and I wish he would remain nameless. It is the object, of course, that was found a few months ago, speeding through the solar system much, much faster than a speeding bullet. Everybody uses the speeding bullet analogy, and in kind of solar system terms, bullets are really slow. So
Yes.
Pretty much everything's faster than a speeding bullet. But anyway, this thing's tearing through our solar system at such a speed that even when it gets so far away from the sun that it doesn't notice the sun anymore, it will still be going at more than 58 kilometers a second.
Wow.
Which is pretty remarkable, all told. And it's been coming through the solar system on this slightly curved path because the sun will deflect it. It's going to change its direction. Coming through, and we've been getting a good view of it, and it's the third ever interstellar object that we've got to see after Oumuamua and Borisov. And it's a relatively small, fairly run-of-the-mill comet, except for the fact that it's a comet that formed around a star that isn't the sun.
Yeah.
And that is pretty awesome and really fantastic. And because we found it so early, people have had a lot of time to study it, get some really good data. Now, unfortunately, from the Earth, it's now ducked out of view. It's passing closest to the sun on the 29th of this month. It's just come very close to Mars, which I'll come to in a minute. But it's swinging in towards its closest approach to the sun, getting more active, all looking good. But it's passing through on the far side of the sun. So it's now, from the Earth's point of view, effectively lost to view for a couple of months. It's ducked out of sight and we can't really see it. Fortunately, we're still going to get something of a view of it, though, because, as I just mentioned, it's just passed close to Mars. Came within about 30 million kilometers of Mars, very roughly speaking, which means if you were on Mars and you weren't worried about getting home, you still wouldn't be able to see it with the naked eye. It's genuinely quite a dim, faint comet from that point of view. So from Mars at the minute, it will probably be about a factor of 100 times too faint to see with the naked eye. But we have all these spacecraft both orbiting Mars and on Mars's surface that can look up and hopefully gather some data. So I saw actually a Reddit thread this morning claiming to show the first images from the Perseverance rover of the comet. Now, I'm a little bit skeptical about this because I saw it on a Reddit thread that someone had posted a random image rather than on the NASA website. But at this close approach, there's been a concerted effort for both the European Space Agency's missions and the NASA spacecraft around and on Mars to actually try and get some data and try and get some images of this object. Now, we've not got any of that back yet, notwithstanding the claimed first image from Perseverance. But this is going to be really, really useful because it allows us to peer at this object as it's getting closest to the sun, when it should technically be most active and therefore there be the most to learn about it, it's giving off the most gas, so there's the most to observe, while it's hidden out of view from our point of view. So that's going to be really, really interesting. It's kind of unfortunate that the shutdown in the US is happening at the minute. I mean, it's unfortunate for many, many reasons, but one of them is that a lot of staff working with NASA are currently furloughed and not able to work, and that will probably delay the results coming out, but it doesn't stop the spacecraft working. They just get on with it. So we will get to see the results at some point, but sadly not quite yet. And however, we're going to get them. It's not the end of the story in terms of spacecraft looking at this thing, though, because there's a couple of other spacecraft that will probably be able to snag some good photos as it moves further through the solar system. We've got the wonderfully named JUICE, which is a Jupiter Icy Moons Explorer, which is currently winging its way out towards Jupiter, that will get a really good view of 3i Atlas over the next month or so, as it goes one way and Atlas goes the other way effectively. Not as close as Mars is to it, but the advantage is JUICE will be inside, closer to the sun than the Comet, so it will be looking away from the sun. Get a decent view now, but it'll get an even better view in about a month's time when it's a bit further from the sun, and can therefore observe for longer without overheating the spacecraft effectively. So we're going to get that data, and it's going to be really interesting to see what comes of this. I think it's going to be one of these cases where the data we get now from Mars, from JUICE, and all the data we gather from Earth will be yielding results that have been discussed for years to come. You know, we'll talk a little bit later about results about Jupiter's moon, about Uranus's moon Ariel, which are based in part on observations that were taken 40 years ago. So these things have a really long lifetime, and it takes a long time for everybody to pick through them to get all of the wonderful juicy bits of gossip out, essentially, all the wonderful information we can learn. So I think all this data is going to give us stuff that will be yielding awesome scientific results, new stories, new discussions on space nuts for 5-10 years to come at least.
Yeah, we're starting to see a lot of that happen these days with new technology, that you'd be able to reanalyze old data and come up with new concepts and sometimes new answers. Another factor that you just mentioned was the photo on Reddit. We are now reaching a point where it's difficult to trust what's happening because of AI, and that's a discussion for another day. But I suppose the way around that is to go to reputable sources. And you mentioned NASA, so that's it's getting like I spend a lot of time on social media, and sometimes I look at an image or a video and go, "Hang on a minute, that's not but it looks so convincing, and that's the problem." So that's 3i Atlas, and we'll have more to talk about in the not too distant future. A few other comets that we might just skim over, within our perimeters, I suppose, or our close to Earth. And the first one is C2025R2 Swan. What's happening with that one quickly?
This one was a big surprise. You know, people like me who are dead keen on going out and looking at comets, they're not really my kind of main professional focus, but they're something I've always loved since I was a little kid as an amateur astronomer, so I get really excited and hyped up when we get a good comet. So I've always got this kind of background awareness of what bright comets are coming up. I check a couple of really good websites I keep an eye on, and I go to those every couple of weeks and just see if anything new's cropped up. And I'm also in a Facebook comet group. Purely as an observer, I've got to say, I don't really post in there because I'm not an expert. And I see people posting in there when new discoveries are made. And normally when we get a comet that gets bright enough to be visible with the naked eye, we get at least a few months' notice. We're getting better and better at finding these things further and further out. And that, of course, is going to get even more the case in the years to come with the incredible Vera Rubin Observatory. But if you go back to kind of our parents' or grandparents' generations, there was this real possibility for a bright comet to just suddenly pop up out of nowhere. And totally unexpected. A really good example of this is back in 1910, when everybody was hyped up looking forward to an apparition of Comet Halley, which appeared in May that year, and was really good that time. It wasn't like 1986 when it was, to be honest, pretty ropey.
It was pretty awful. I remember that.
Yeah, that was the worst apparition of Comet Halley for 2,000 years. It will be better next time round, and just to make you and I feel old, it's now closer to the next apparition of Comet Halley than the last. So it is nearer to 2061 than 1986. But back in 1910, everybody was hyped up and looking forward to Comet Halley, which was going to put on a really good show. And then in January 1910, suddenly this comet was discovered by miners in the Transvaal when they were leaving the mine first thing in the morning in South Africa, visible with the naked eye as bright as the brightest stars in the dawn sky before sunrise. That was the Great Comet of 1910, and it was first visible when it was at perihelion, because it sneaked up on us from the far side of the sun, effectively.
Yeah.
And now that was really quite close to the sun. It was visible in broad daylight for 4 days continuously. That's how good it was. One of the brightest comets of the 20th century. Which brings us to this one, 2025 R2 Swan. It is not as bright as the Great Comet of 1910. If it was, everybody would know about it.
Yes.
But back, bizarrely, about 3 weeks ago now, it went from being unknown to being the brightest comet in the night sky at the time it was discovered, which is unheard of. And it was almost naked eye visibility when it was discovered. It was about magnitude 7.5, so a factor of 2 to 3 times too faint to see with the naked eye if you've got good eyesight and a really dark sky. It is still on the cusp of naked eye visibility. Some of the observations people are sending in of it report it being just bright enough to see with the naked eye, others just a little bit too faint. This one is still better seen for people in the southern hemisphere than the northern hemisphere, which seems to be a recurring theme for comets, but is not always the case. And there's been some absolutely glorious photos coming of it, particularly in the first few days after it was discovered, actually, because it was discovered very near to the bright star Spica in the constellation Virgo, near Mars, which was close to Spica at the time. So you've got these glorious photos taken by some of the world's best comet photographers that show this beautiful comet with a lovely long iron tail next to the bright red star Mars, the bright red planet Mars, bright blue star Spica in Virgo, and just putting on an incredible show. And it's not brightened much more because we discovered it when it was about as bright as it was going to get, but it's hovering on the edge of naked eye visibility, will remain so for another few weeks because it's been moving away from the sun but towards the Earth, and that's been balancing out effectively.
Yeah.
So that's been putting on a fabulous show, particularly for astrophotographers down here in the southern hemisphere. Seems that it's a comet that comes around about every 1,000 years or so. There were even suggestions that the Earth could get a minor meteor shower from this comet around today or yesterday as we cross where the comet is going to be in a few weeks' time. We cross its orbit today. That seems unlikely, although totally in passing, I have seen notifications that there has been a brand new meteor shower observed for the very first time just over the last couple of weeks, deep in our southern sky, by these old sky camera networks. Now, probably not related at all, but it's interesting how all these things happen at once. So that's been a really interesting comet, and it's a real reminder that we might not necessarily get really good warning the next time we get a really good comet. We probably will, especially with Vera Rubin. But there's always a possibility that something like this will come along where, effectively, due to the quirks of celestial mechanics, it approaches the sun, swinging in on a curved orbit, whilst hiding behind the sun from our point of view, staying within about 30 or 40 degrees of the sun in the sky, which means it's lost in the twilight glare. And it only pops up as it swings around the sun to our side of the sun. That's what's happened here. That's what happened with the Great Comet in 1910 as well. It just happened to come in such a direction that as it moved, it stayed hidden. You know, a bit like a small child playing peekaboo, I guess, kind of trying to stay hidden behind the thing as you move around.
Yep. Okay, so that's Swan, and it's around for a little while longer. The other two that are in the news at the moment are A6 Lemon and R3 Pan-STARRS. What's happening there?
A3 Lemon is one that was discovered back in January. So with these comet names, they're a little bit like a calendar. They can tell you exactly when comets are found. So if you hear a comet described as C/2025 A6, which is what we've got with Comet Lemon, the C tells you that it's a comet that is not a short period comet. It's not been seen at multiple apparitions. In this case, it's a comet with a period of more than 1,000 years, but less than 10,000 years, probably about 1,400.
Mm-hmm.
The 2025 tells you it was discovered in the year 2025, and the letter tells you which fortnight of the year it was discovered in. So the letter A here tells you the first 2 weeks of January.
Right.
So this comet was found right at the start of this year, and it looked like it was going to be promising, but it wasn't heralded as being the equivalent of kind of Comet Atlas we had at the start of the year, or Comet Chinchin Atlas last year, which were great comets. I'd classify them as. They were really bright, easily visible from even brightly light polluted areas. They were really spectacular. This comet is currently best visible from the northern hemisphere. We don't really get to see it down south just yet, but it's swinging into perihelion. It's currently about the same brightness as the comet I just discussed, Comet R2 Swan. But this one is still brightening, and at its brightest, it will, unless it does something unexpected. You know, comets, famous saying says, comets are like cats, they have tails and they do whatever they want.
Yes.
So there's always a chance that this thing could undergo a fragmentation event and brighten by a factor of 100. That kind of thing does happen. Not necessarily all that likely. But if it continues brightening as it currently is, and it's behaving really well at the minute, it will probably at its brightest be comparably bright to the Andromeda Galaxy. So visible with the naked eye from dark sky sites if you know where to look, but not visible from the middle of light polluted Sydney or Brisbane or somewhere like that, unless you've got binoculars. But it's going to be the brightest comet in our sky since Comet Atlas back in January. It's going to be a fairly good sight. Again, there are some absolutely astonishingly good photographs coming in from the northern hemisphere of this. It's really photogenic. And it's going to be above the threshold for naked eye visibility for about 2 months, building up to that peak and then fading away again. So it's going to be a really good sight. Currently, it is best visible from the northern hemisphere. I believe it's currently quite high in the northern sky, edging towards the southern outskirts of Ursa Major, that kind of part of the sky. But it's then going to start ducking southwards, and by the time it's at its brightest, which is going to be the start of November, it will be visible from both hemispheres, albeit, I think, easier to see from the northern hemisphere still. But this is going to be a naked eye comet. Naked eye caveat, not that spectacular, but visible if you know where to look. For those who go out and look at comets and that, therefore, it's probably a little bit brighter than Pons Brooks was last year. Pons Brooks was, capped as the Devil's Comet and all those kind of weird names that these things seem to get in the media. If you saw that one with the naked eye, this comet should be a bit brighter than that and a bit easier to spot, but it's probably a really good opportunity for people to dust off their camera gear, do a little bit of planning and go take some photos. So it's going to be pretty good. And nobody complains about a naked eye comet.
No, they don't. And R3 Pan-STARRS, I'm guessing from its name, is a very recent discovery.
It is. This was discovered very, very recently, and we still know surprisingly little about it, actually. I mean, if I go to the place I normally look at the light curves for these comets from, where it aggregates all the observations and tries to predict forward how bright it's going to be, that has a really nice light curve for this object. But it has no observations on the light curve at the minute. So this is very new. It is still very faint. I mean, with this one, we're talking about something that's probably a factor of 50,000 times too faint to see with the naked eye at the minute. Very recent discovery by that wonderful automated search facility on the top of Hawaii, Pan-STARRS. The reason this has got my attention is that it is going to pass incredibly close to the line between the sun and the Earth, which we've seen with those two great comets we had in the last 12 months. And when you get an object that passes directly between the sun and the Earth, if it happens to be a particularly dusty comet and shedding a lot of dust, there's a phenomenon called forward scattering, which we in Australia are fairly familiar with on dusty days because near sunset the sky is unbearably bright and it's awful driving west at sunset, which is something people in Toowoomba are very familiar with because our roads are kind of east, west, north, south.
Yeah.
And so around the equinoxes, you drive towards the sunset and get snowblind effectively. Skiers are familiar with it for the same reason, on a kind of day where there's a lot of small ice crystals in the air, the sky can be very bright in the direction of the sun. Mm. This phenomenon of forward scattering can make comets brighten by more than a factor of 100, depending on the orientation, when they're close to the sun in the sky. Or when they're close to that line between the Earth and Sun. Now, this object, Pan-STARRS, it looks like it's a fairly small comet, but we've not got much information about it yet. But its orbit's fairly well constrained, and it is going to come very close to the Sun in the sky from our point of view. For a time, people were even suggesting it could transit the disk of the Sun. Even though we wouldn't see anything because it'd be too small to be visible, it could pass so perfectly between us it would cross across the disk of the Sun from our point of view. What that all means is that if this comet becomes fairly active, there's a chance that it could become quite bright in April next year. Now, how bright is utterly unknown at the minute, but it's worth flagging up because it's an interesting one. The light curve I'm looking at as I talk about this is in all honesty, with the lack of observations, we've got something of a fiction. It could get a lot brighter than this or a lot fainter than this. But it suggests that without this forward scattering process, this comet would be too small to be visible with the naked eye. But with forward scattering, it could get as bright or brighter than Comet Lemon. So it could get brighter than the Andromeda Galaxy, albeit when it's quite close to the sun in the sky, and therefore it could be visible to the naked eye for a week or two. Now, if it turns out to be a larger and more substantial comet than those first observations suggest, that all ramps up and it could be even better. So there's a small chance, I'd say, that this thing could be visible with the naked eye in April, but it's just, again, once again, a reminder of as we get better at these kind of all-sky surveys, we're going to find interesting comets earlier. We're eventually going to get to the point where an object like Comet R2 Swan that we've got at the minute can't surprise us, because we'll get our telescopes good enough that we'd find it a really long way away before it hides behind the sun. Okay. And so, it wouldn't surprise me if the next great comet was found months ahead of time rather than weeks ahead of time, and we get prior notice. And because it's observed that early, we might have this level of uncertainty in an object that's a bit brighter than this, and people will either be calm and cautious or hyperbolic and excited, and then we get to see that's part of the fun of it.
Yeah, indeed. Okay, so plenty, or potentially plenty for sky watchers to look forward to, and a lot going on at the moment. And while you've been talking about those comets, I've been looking up some of the media pictures, and it's interesting to see that the quality of the outlet dictates the genuineness of the photo. Let me just say that. This is Space Nuts with Andrew Dunkley and Jonti Horner. Let's take a break from the show so I can tell you about our sponsor, NordVPN. With NordVPN, you can explore the web securely and privately no matter where you are, whether you're streaming space documentaries, downloading data from the International Space Station, legally of course, or just browsing from a coffee shop. NordVPN has your back. Fast connection speeds, no data logs, and protection across all your devices, including your smart TV, plus access to content from around the globe. It's like having a wormhole to the internet. Sorry about that. Without the black holes. Haha. Right now, Space Nuts listeners get an exclusive deal. nordvpn.com/spacenuts. Huge savings, plus an extra 4 months free. That is fabulous. nordvpn.com/spacenuts helps you stay protected online and gives you everyday access without any fear that your private data will be stolen. That's nordvpn.com/spacenuts. And don't forget to use the code word spacenuts at the checkout. nordvpn.com/spacenuts. Now back to the show.
0G, and I feel fine.
Space Nuts.
From comets to meteor showers, and there's a few making the news at the moment, Jonti.
It's a good time of the year for meteor observers, particularly in the Northern Hemisphere. Whilst comets seem to get a slightly better deal in the Southern Hemisphere over long periods of time, the Northern Hemisphere gets the better of the meteor showers. We're getting a fair bit of coverage already about the Orionid meteor shower, which is already active but is building to a peak around the 20th, 21st of October. Now, the Orionids are a meteor shower that's caused by Comet Halley, which has been whizzing around the sun on its current roughly 76-year orbit for thousands, if not tens of thousands of years. It's a very big cometary nucleus laying down lots of dust, and that dust has spread out to such an extent that every year the Earth crosses through that tube of dust left behind by the comet on two separate occasions.
Yeah.
We get the Intra-Aquariid meteor shower in May, which is one of the year's best meteor showers, but it's really hard to see, and you need to be up in a couple of hours before dawn to see anything, and that favours Southern Hemisphere observers, so it's not as well known and not as well observed. And then you have the Orionids in October. And the Orionids are not as good as the Intra-Aquariids. They're probably in the second kind of tier of meteor showers. So you've got the big three in the form of the Quadrantids in January, the Perseids in August, and the Geminids, which are the best meteor shower in a typical year in December. And they're reliable every year, really good rates, and they're the ones that you tell your friends who are not into astronomy to go out and look at because they're good enough that someone who's not that excited already will still see a good show. The Orionids are like the next tier down. They are if you're someone who's really keen on astronomy and you're happy to spend an hour or two sitting out in the middle of the night, you'll see a reasonable number and they're lovely to see, but they're probably not active enough that someone who's not that keen on astronomy will get a real buzz out of it, if that makes sense. So if you're somewhere in Northern Europe and North America where you've got long dark nights at the minute, and you were out all night, you might see 15 or 20 of these per hour in the early morning hours in late October, the kind of 19th, 20th, 21st, 22nd. Mm-hmm. From Australia, the rates are a bit lower because the point in the sky these meteors come from, the radiant, is lower in the sky at its highest. And geometry means that, therefore, the same number of meteors are spread over a larger volume of atmosphere. So you'll see a smaller number of them from wherever you're sat. But you can still see, if you're in kind of the top end of Australia, I'd say 10 or 15 per hour. If you're down at the southern end, a little bit less than that. The further south you go, the worse it'll get. This year, though, is particularly good because it's new moon. And so what that means is you've got ideal viewing conditions. Okay. You don't have the glowing orb of doom scattering light in the sky and basically blocking the view of all the interesting stuff. I've always been, as an amateur astronomer, that side of my life, frustrated by the moon because it stops us seeing all the good stuff. But that's particularly true of meteor showers. That's the Orionids. They're getting a lot of coverage. What I would say with it is, unless you're a really avid meteor observer or unless you're going out anyway, don't buy into the hype. There'll be a lot of overblown articles, and I'm seeing them already from some of the less reputable media outlets online, talking about the skies falling and this will be the best thing you'll ever see. And that just sets people up for disappointment. It's always a little bit sad. But if you do want to go out and see the Orionids, around the 20th of October is the best time. Unlike most meteor showers, the Orionids and the Eteroquarids in May, both these Comet Halley meteor showers, have quite a broad maximum. So if it's cloudy on the night of the peak, you'll still get a decent show for 2 or 3 nights either side. It's a much flatter plateau, effectively. And they do sometimes throw a bit of a surprise our way. They are fast meteors, have a tendency to produce quite a few bright ones as well, and you see them best if you're out in the early hours of the morning after midnight. That's kind of the best time, with the best rates being just before dawn. But they are visible from about 10:30 at night.
Okay. Now, the other meteor shower that you wanted to talk about that could be worth a look is the Draconids. I don't know much about this one.
This is a really fun little shower because it's illustrative of how meteor showers are really changeable over time. The way a meteor shower forms is you've got a comet going around the sun, and a comet is a dirty snowball, a snowy dirt ball. So when it's far from the sun, it just looks like an asteroid. Nothing's happening. It's a tiny speck of light, a few kilometers across. When it gets close to the sun, the surface gets hot, and all the ices on the surface sublime. They turn to gas, erupt from the surface in jets because they only sublime if they're exposed to enough heat to get off, and a lot of the surface is caked up and blocked up. So you get these little active areas casting jets of material into space and carrying with them a lot of dust. So comets, when they're closer to the sun, shed gas and dust, and that's why they get the coma and the tails that make them brighter and easy to see and so spectacular. The dust that they shed is ejected from them at speeds of meters or tens of meters or maybe hundreds of meters per second, but typically 1 or 10 meters a second, while the comet's going around the sun at a speed measured in tens of kilometers per second. So that means that the dust will end up moving on essentially the same orbit as the comet. It won't move onto a drastically different orbit. The smallest grains of dust are blown away by the sun and the solar wind and radiation pressure, but the bigger bits of dust kind of stay moving around the sun on an orbit similar to that of the comet. But because of that ejection speed, some of the dust grains move on orbits that have a shorter period than the comet. Some move on periods that are slightly longer than the comet. So over time, they spread out ahead and behind the comet in its orbit until eventually the orbit is clogged with dust all the way around. So if you go across the orbit when the comet isn't there, you'll still run into dust because there'll always be something there. Then when you get the Earth running across one of these orbits, if they intersect in space, every year we'll go through that dust and we'll get a meteor shower. Now, comets' orbits are constantly changing, and that's particularly true of a family of comets we call the Jupiter family comets, or the short-period comets. These are comets captured by Jupiter, flung into the inner solar system, moving on orbits that are kind of 5, 6, 7 years long. So you'll get a comet will be nudged, dropped onto a new orbit, and it will start laying down dust on that orbit. But it might not be there particularly long until it's flung onto a different orbit. The orbit's constantly being tweaked and changed. That means that you get these dust trails that build up over time, but you can even orphan them. You can take the comet away and the dust trail remains, which is the case of some of our meteor showers. It also means, though, that when a comet is relatively newly placed onto a given orbit, that orbit won't have fully clogged up with dust yet. So most years when we cross where that orbit will be, we'll get very few meteors because the dust just hasn't had time to spread out yet. But if you catch it on a year when the comet is relatively nearby, you might run into dust. The final little piece of all this puzzle that I'm talking through is that dust that was emitted at the last few apparitions of the comet will not have had time to spread out a huge amount laterally. So you get these almost like javelins, very thin, very long filaments of dust that are much denser. And if the Earth goes through one of those, suddenly you can get a really big meteor outburst. And instead of getting 1 or 2 meteors an hour, you might get hundreds or thousands.
Wow.
So that's a lengthy bit of background exposition to kind of explain what's happening in the background here. The Draconid meteor shower is one that kind of shot to fame in the year 1933, when there was an incredible meteor storm where people saw literally thousands of meteors per hour. That's more than 1 a second. Raining down, absolutely incredibly spectacular. All radiating out from this point in the night sky near the northern hemisphere constellation of Draco. There was a slightly less spectacular but still very intense meteor storm from this shower in 1946. And since then, most years, you get 2 or 3 meteors an hour from this meteor shower. They're very slow meteors. They're typically fairly faint as well. But there's always a little bit going on. But every 6 years or so, the comet comes back to perihelion and there's a chance of us getting an outburst. Now, whether we get one or not depends on the gravity of all the other planets pulling the comet's orbit and these debris streams around. Sometimes they'll miss us underneath or they'll miss us above and we don't run through them. But it's become an active thing of trying to figure out what's going to happen next. Could we ever get another meteor storm from this shower? Now, we've had a few outbursts that are not storms, but are good. A few years ago, there was an outburst where there were 100 meteors an hour visible for a couple of hours, which is a pretty good meteor show.
Yeah.
That's led to people using this meteor shower as a really good testbed for how we model how these things work, trying to improve our computer models of how all the dust moves, where it's all going to be, so that we can predict forward and say what's going to happen at the next apparition. And a paper came out literally just a couple of days ago that explored this in some depth. It's from some of the leading meteor astronomers in the world doing modeling of the Draconids. And what it suggested is that this week, literally the week that we're recording this, there is a potential for the Draconids to have a fairly good outburst on Wednesday night into Thursday morning Australian time. So that's around the 8th of November. The evening of the 8th of November, Universal Time, early hours of the morning, October. 8th of October, Universal Time, early hours of the morning of the 9th of October for us here in Australia. There'll be a bit of an outburst. Now, this is probably not going to be an outburst that's particularly spectacular visually. Reason for that is it's full moon. So it brings us back to the moon getting in our way and spoiling all of our fun. If the full moon wasn't the full moon, it's likely that this outburst could be somewhere between 30 meteors per hour and 100, maybe even 200 per hour. But the Draconids tend to come in fairly slow and they tend to be small, faint meteors. So almost all of them will be lost to the naked eye in the moonlight, unless they're not, because this is just a prediction, so something could happen that is better than we expect. What's most likely to happen, though, is that people will see a few meteors through the moonlight, and that will tell you there's a lot more going on than you can see. But the astronomers doing observations with radar will see an outburst, and it will probably be the strongest radar meteor shower of the year. So these are people almost doing kind of beyond the horizon radio listening. One of the most common ways you can listen to meteors in radio wavelengths is to look at an angle low to the horizon when you're in a country where there are other countries far enough away that their radio broadcasts can bounce off the ionized trails left behind by the meteors 80 kilometers up and bounce back down to you. So obviously for a lot of places, this just doesn't work because you're looking out over the ocean. But for people in Europe or people in North America, quite often there's a city at about the right distance. It's quite a big bit of wiggle room. That if you're pointing your detector roughly in that direction, every time there's a meteor, you'll suddenly get this reflective ionized trail 80 kilometers up, radio waves that would have normally escaped the atmosphere and gone on into space will bounce off that and bounce down to you, and you'll get a little burst of radio noise. And so that means people can count meteors. And it's likely that this draconic outburst will be confirmed not by people looking with the naked eye, but by people listening with radio antennas. And they're saying in terms of radio signals, you could get more than 1,000 per hour. So it could be a fairly intense outburst, just not one that is really visible with the naked eye. The reason it's worth flagging up, though, is it's a good insight into how we do the science of this, that kind of beautiful interplay of theory and experiment and observation, where we predict something, we test that prediction, and that allows us to improve our models to make the next prediction even better. But it's also worth flagging up because the one prediction you can make is that all predictions will be wrong. And so while we're saying that it'll probably be only 40 or 50 per hour or 20 per hour with the naked eye, and the moon will hide most of them, you can't rule out that it'll be better than that. So if you're up in the early hours of the morning on Wednesday night into Thursday morning, it's worth having a bit of a look. The forecast peak is forecast to be at 3 p.m. Universal Time, between 3 and 4 p.m. Universal Time, which is Greenwich Mean Time. So you can work out from that what time it'll be for you. For many people, it'll be in the daytime. So sorry, but this time kind of favors people in East Asia and Australia, that kind of area. So we might see something, we might not, but it's worth a look.
Okie doke. Yeah. If you want to read about that, you can do so at the harvard.edu website or go to the archive website where the paper was published. And I'd read out the whole thing, but it's you'll never remember it.
I was going to say one thing I should mention with that is the Draconids are best seen from the northern hemisphere. So if you're in the southern hemisphere and you want to see this nearer to the equator, you are, the better. And in reality, I'd say that people south of the line, about at Brisbane's latitude, it's not even worth bothering because the radiant will be so low in the sky that you will see nothing at all. Really is more of a northern hemisphere thing. So I want to make sure that we don't get somebody down in New Zealand going out looking for it and saying, I saw nothing. But, well, of course you saw nothing because you can't see anything from there. I'm really sorry.
Yes, that's the way it goes, though. That's the way it goes, yeah.
Yes.
All right. This is Space Nuts with Andrew Dunkley and Professor Jonti Horner.
Okay, we checked all 4 systems and team with a go.
Space Nuts.
All right, let's move on to Uranus and the moon Ariel. This is a really fascinating story about what might have been, in its past, a hidden ocean on a rather small object.
It is, and it's part of this ongoing journey of discovery that we're getting, where fundamentally the kind of world that I grew up in as a kid excited by astronomy in the 80s and 90s just isn't the same anymore. I was growing up and the kind of accepted wisdom was that water was incredibly rare and liquid water particularly rare, and therefore life would be uncommon in the cosmos. So this was one of the kind of centerpieces of the rare Earth hypothesis, which basically said don't even bother looking for life elsewhere because we're all there is. And I've never particularly put much stock in that idea, but what we've seen in the last 30 years or so is that water is actually incredibly more common than people would have thought. And that's not a surprise. You know, if you look at the universe as a whole, hydrogen is by far the most common atom. Oxygen is the third most common atom. And if you put them together, you get water. And we see in the outer solar system, we see in the form of these comets we talked about earlier on, water ice is incredibly abundant. And in fact, of the solid material in the solar system, water ice is by far the largest amount of mass of everything once you're out at Jupiter's orbit and further out. All the icy moons, all the comets, all the trans-Neptunian objects are basically lots of water ice with a bit of other stuff going on. So solid water is really common. Liquid water, though, people said, well, we've got a lot of it on Earth, but elsewhere it's not that common. And then we found liquid water in Mars's polar caps, and we've found all these deeply buried subsurface oceans, the kind of poster child of which is Europa. And, you know, even in the kind of wonderful films, you know, all these worlds are yours except Europa, attempting a landing there. That whole kind of thing. So we found all these subsurface oceans, and the more we look, the more we find them. There was a story earlier this year that the dwarf planet Ceres in the asteroid belt had a subsurface ocean in the past.
Yeah.
And now we come to Ariel. Ariel is one of Uranus's moons, and Uranus's moons we got some lovely images of from the Voyager 2 spacecraft back when I was a wee bairn, back in kind of 1985, 1986 time. Voyager 2 flew past Uranus as part of its grand tour of the outer solar system. And as we always say, it flew past faster than a speeding bullet, so it didn't have very long to hang around and take images. And because Uranus is tipped over on its side, and its moon's orbit above Uranus's equator, they're all tipped over on their side. So you had basically midsummer at Uranus there, and all of these moons had one hemisphere illuminated and one hemisphere dark, which meant that as Voyager 2 flew through, we got all these beautiful pictures of Uranus's moons, but for all those moons, we only saw one side of them. We saw the southern hemisphere illuminated by daylight, but we didn't get to see the other side. And we saw these really unusual objects. Miranda's kind of the most famous for this, which almost looks like somebody's taken a moon and smashed it apart with a hammer and then rebuilt it haphazardly. You've got all these very different features next to each other. It looks really odd. Ariel is a bit bigger than Miranda and also looks really odd. It's got areas on its surface that are clearly very, very old. They're fairly relatively low albedo. They're not that reflective, and they're incredibly heavily cratered. But it also has these areas that are much more reflective, much smoother. They have far fewer craters. And they've also got these incredibly large canyons, fissuring, valley-type features on them. Mm. And again, it looks a very odd world. A bit like Miranda, you've got very different surfaces relatively close to each other that look very different to one another. Geologically, they look like they've got very different histories. That's 40 years ago, and this is a really good example of what we talked about earlier, where data from the past continues to have value as our tools improve, so we can better understand it. Because a new result that's come out in the last couple of weeks is a result of really impressive computer modeling, trying to figure out what's going on with Ariel. Why does it look so unusual? Typically, when we see smooth surfaces with far fewer craters, we consider them to be younger, because impact craters are happening all the time, and so the longer you have to be exposed to space, the more craters you'll get, which leads to this kind of science of crater counting, where you can estimate the age of a surface by seeing how many craters it's got per square kilometre or whatever.
Yeah.
So the fact that Ariel's surface is in places smoother and brighter suggests that that surface is younger and that there's been significant resurfacing there. And the idea is that there was probably cryovolcanism, where molten water was erupting over the surface and then freezing, in just the same way that molten rock on Earth erupts and then sets in volcanic eruptions. But that was a bit speculative. What this new modelling has done is it's looked at the history of the orbit of Ariel and suggested that in the past, Ariel's orbit was probably a little bit more eccentric than it is now. Probably an eccentricity up to about 0.04, which is a bit more eccentric than the orbit of the Earth, but less eccentric than the orbit of Mars. On an orbit that is just slightly eccentric like that, Ariel, which is sandwiched in between all these other moons and is near a pretty massive planet in the form of Uranus, would have been subject to fairly intense tidal forces that would have squashed and squeezed it. And that's very much equivalent to what's happening in the Jupiter system with Io and Europa. These moons that are squashed and squeezed by Jupiter's gravity and the nearby moons, which dumps a lot of heat into the interior of these moons, keeping them hot, driving volcanism, allowing that deeply buried ocean in Europa, well, say deeply buried, probably under about 10 kilometers of ice, to stay liquid because there's an internal heat source driven by this tidal heating.
Yep.
What this work has said is that Ariel 2 probably had a lot of internal heat from tidal heating. It's a big object that's primarily made of water ice, and when you heat water ice, what happens is it melts. And so the idea is that for a very long period of time, probably hundreds of millions of years, if not billions of years, buried under the surface of Ariel, and possibly even relatively shallow at some times, was this ocean of liquid water that, again, just like Europa, probably contained more liquid water than there is on the entirety of the planet Earth.
Wow.
That water would have behaved like the mantle of the Earth, with volcanic eruptions of water breaking through cracks in the surface, resurfacing these areas of Ariel, giving us the clues that we see now, probably more than 1 billion years after this ocean froze solid. Ariel's orbit settled down, tidal forces lessened on it, it cooled down, everything froze solid. But we're left with these fossilized clues that are evidence of this much more interesting past, potentially, when you have this moon with a soft central liquid center.
Yeah.
And it's interesting in itself. It's interesting because of this interplay between observation and theory, and how it shows you that observations may not bear fruit for decades. It might be that the observations we make now are not fully understood for 10, 20, 30 years as our technology and our modeling and our theories develop in that time. But it's also interesting from the whole question of, are we alone in the universe? Is there life elsewhere? Because it's reminding us that liquid water is much more commonplace in the cosmos than we think it is. Now, finding life on buried oceans is challenging in the solar system. It's not really something that's feasible going forward, looking at planets around other stars. But it is a reminder that there might be an incredible diversity of potential habitats for life to become developed and thrive all through the solar system, all out there in the cosmos. And certainly in the solar system, these are the kind of locations that we can visit. There's a really growing push among planetary scientists that Uranus should be the next place to get a probe. We've seen incredible science done by orbiters like Galileo and Juno that went to Jupiter, like Cassini that went to Saturn. But for Uranus, we've only seen one face of the planet, one face of all its moons, as we flew through on a drive-by, essentially. And the argument is, if we could send a spacecraft there that did for Uranus what Cassini did for Saturn, what Galileo and Juno did for Jupiter, there is so much we'd learn. And Uranus is such an oddity among the planets with its satellite system, with everything all tipped over. It's got a very different history to the other planets. There's some violent event in the past, quite possibly something more massive than the Earth hitting Uranus, knocking it over, disrupting the satellite system, giving us the moons we see as a secondary satellite system. The original moons were destroyed, formed a disk of material, and new moons formed from them. It's a very wonderful narrative that is our best explanation for what we see, but it may not be the right one. And the only way we'll find out, the only way we'll learn more about this is to go there, send a spacecraft there. So this is so exciting for people that it's actually the top priority of the Planetary Science Decadal Plan in the US, trying to argue for funding to build a mission. Now, if that mission was approved, it will probably be another 20 years before it gets there, if not more. And that's one of the challenges that people face, because you are dealing with governments that change on timescales of 3 or 4 years, who often seem to have the policy that whatever the previous government decided was wrong, so therefore we need to cancel it. And you've got to navigate those waters to try and get a mission to happen where the development alone can be 10 or 20 years. So it's really challenging, especially in the current climate. But the hopes of planetary scientists across the world are that at some point, a mission like this will get approved and we'll get to go back there and find out what's actually going on.
Yes, indeed. But what I'm finding fascinating is that the more we look and the more information we gather and analyse, these ice moons, these subsurface ocean moons in the outer solar system are starting to become the norm, really. They're identifying more and more of them, or at least they're suspicious that some of them are there that we weren't thinking about before that are starting to show those kinds of tendencies. And here's yet another one. So there's plenty to look for at around that where the gas giants are and beyond. Really fascinating stuff. Now, finally, let's do this one. Asteroids controlled by Venus and what that means for Earth. Our sister planet might start throwing stuff at us in a few thousand years' time.
Oh, absolutely. This is a story that's all about few objects that have been discovered relatively recently that are very, very hard to spot, that fall under the broad heading of near-Earth asteroids. They're things moving in the inner solar system on unstable orbits. And obviously, we've seen Deep Impact, we've seen Armageddon. We know that these things can pose as a threat. And there's a big growing push to find them and to peer through the growing numbers of Starlink satellites that make it harder and harder for us to do that. And it's one of the things Vera Rubin's going to be great at. Vera Rubin's going to be great at everything, to be honest. But it'll be a fabulous near-Earth asteroid finding machine. But these ones are going to be challenging even for Vera Rubin. These are asteroids that spend their entire orbits closer to the sun than us. I've seen them described as apoheal asteroids, as their family name. These are things where even when they're furthest from the sun, they're still closer to the sun than we are. And what that means is that they're always, to some degree, lost in the sun's glare. They're hard to spot. Now, there's a growing population of these that have been found that are moving on orbits with a similar orbital period to Venus, maybe even trapped in one-to-one resonance with Venus. So they complete one lap of the sun in the time it takes Venus to complete one lap. And we found a few of these. All of the ones we found are on relatively eccentric orbits, eccentricities of about 0.38 or greater, which means that the point at which they're furthest from the sun is 38% bigger than their mean distance, their semi-major axis, and the point at which they're closest to the sun is 38% smaller, basically. So if you know the semi-major axis, call that letter A, the distance between these objects and the sun at their aphelion, their furthest point, is equal to 1 plus the eccentricity multiplied by semi-major axis. So an eccentricity of 0.38 gives you 1.38 times the semi-major axis. That's basically the way this works out. So what that means is if you're on an orbit that is a semi-major axis the same as Venus, which is a little bit more than 0.7 astronomical units, if you have an eccentricity of about 0.38 or more, you'll get close to the Earth's orbit when you're furthest from the sun. And that means that you're further from the sun in the sky and you're easier to find. So we've got an observation bias. If we find a lot of objects then in the one-to-one resonance with Venus that are on eccentric orbits, we can suggest that there are going to be far more of them that are not on eccentric orbits because they're harder to find. So we're finding the low-hanging fruit. So the idea is that there is a population of hundreds of these objects, possibly even thousands of them, ranging in size up to hundreds of meters, maybe even a few kilometers in size, that are near-Earth asteroids that have evolved quite a long time in their orbits, moved into the inner solar system and bounced down to Venus. And they're kind of held in a freezer there. They're kind of held out of our way in a reservoir, not to be worried about. The new work is that people have done some orbital simulations of the kind that I do in my day-to-day life. And they've looked at what will happen to these things over time, because moving on orbits in the inner solar system is an inherently unstable situation. You're vulnerable to the whims of the gravity of all the other planets, and that means your orbit gets bounced around. You have close encounters with the planets, and that means that things are not stable in that one-to-one resonance with Venus on really long timescales. They'll eventually escape and move around. And what this study has shown is that for these objects that we currently cannot see, they're currently, most of them, hidden from view, they are on orbits that can evolve to become Earth-crossing once again, maybe even within just a few thousand years. And so that this is a previously unthought of reservoir of potentially hazardous asteroids that we can't easily detect with our normal methods, and that Vera Rubin, with all its brilliant abilities, will be challenged to pick up. And so it's flagging up another area of objects that they don't pose a threat to us right now. Probably. There might be some of them on orbits that just reach the Earth, so they could do, but most of these don't pose an immediate threat, but they pose a longer-term threat. And the kind of, I guess, punchline of all of this is that we need to become better. We need to be creative and think about how we can find asteroids like this that are hidden in the sun's glare, what we can do in order to try and quantify the ones that are there and figure out if any of them pose a threat. That's kind of their punchline. And I think it is just a really great reminder of the fact that we always think we now know so much. We know so much more than we used to do, and you always have this niggling impression at the back of your mind that our knowledge is almost complete. There are no surprises still to come, and that's just not the case.
No.
Part of the reason that I love science, part of the reason that most scientists still do their job, is not because we know everything, but because we know nothing. Yeah. We've still got so much more to learn, and it's the surprises, it's the unknowns that really motivate people and get people excited. And this is just a really good example of that here's all these objects that we weren't even talking about 10 years ago that are a potential threat to us, and we need to learn more about them. How do we do that? And that will drive technology and exploration in the years to come.
Yes, indeed. And if we've got a few thousand years of wiggle room before it starts throwing rocks at us, we may be able to put probes out there to monitor it and get those early warnings. So we may develop the technology to defend ourselves down the track. But if you want to read about that, it's the paper is available through Astronomy and Astrophysics, the journal, or you can look at it on the space.com website. Fascinating stuff. And Jonti, thanks for joining us. Great to have you back for a few weeks, and we'll catch you on the next episode.
Look forward to it. Thanks for having me back.
Professor Jonti Horner, Professor of Astrophysics at the University of Southern Queensland. Thanks to him. And I would have thanked Hugh in the studio, but he forgot to set his clock forward for daylight saving in New South Wales yesterday and couldn't join us. And from me, Andrew Dunkley, thanks for your company. See you on the next episode of Space Nuts. Until then, Bye-bye.
Space Nuts.
You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.